Okay. So the maximum likelihood, we need a likelihood function, right? So the likelihood function, we need a function. Okay. Okay, Moses, thank you. Okay, so we need the data which we are taking as S, and then we need some parameter values, right? Okay, so that's what we need to do. Now, so I can write this as, so first of all, if I want to use this, I'll go and look for D gamma. Yes, that's the easiest. But remember that you cannot use the same principle when you don't have a density function in R. So here, X is our X, right?
Yes.
Okay. And then the shape will be maybe the power 1. Is that okay? Because we are going to input in a vector. Then the rate, we can take it out and use scale. That will be 2. Oh no, we are actually using the rate. Or yeah, let's go and check. Okay, a scale. Yeah, so it's rather scale. So okay. Log false, we can take it out. Not necessary. So I need to make a socket at the back. Okay, but remember that this will give you the density. I'm still muted. What happened? Okay. So what we need the negative of the, so we'll do negative sum, right? And the log, right? Is everybody okay with this?
Yes, sir.
Okay, so I think I can just return it. I don't even need this. Yes, so I just put it like this. Okay, so that's the log likelihood. Negative log likelihood. So maybe neg like will be better. Okay, so then we need to pass this to an optim function, right? So if you like, you can put all of them in a function. So that does a, so mom, no, this is not mom, mle dot gamma will then be equal to function. This function should take what? X and what? Pi, right? And it should call optim, so mle should call, let's say, optim. Okay, and you can get the help files for optim so that it becomes easy for you to not make a mistake. So optim, we copy all this. Of course, we will not need all of them. Okay, so what is our par? It is going to be the par of it. Yeah, so we can, of course, we are going to give it something, C, when we call the function. So it's okay to put par over there. Then the function should be what? Neg log like. We don't have to worry ourselves with the gradients. The method, we can leave it like that. Now the mid, we don't need even the lower and upper. If we were to do it, we can, I think BFG and LBFG, they need those lower limit, upper limit. So in this case, if you want a lower limit for the shape, it will be negative. Then the upper will be positive infinity. But for the scale, it will be 0 for the, so if you have to do that, it has to be this. So this is what I mean. So in some cases, you will have, let's say, 2 or 3 of the, if you are doing the first one will be negative, but the other one will be 0. Then here, you will have, let's say, replicate inf 2 times, something like that, or C inf, whichever way. Yeah, but that's when you are using the box constraint, where you give it lower limit, upper limit. So you remember, the scale cannot be negative. Do you get it? So it must be positive. That's why we give it, but we won't need it here, and the rest we can just, delete all of them. So like this, Haitian, maybe I'll need it. So the Haitian I can say is true, so that you can get a Haitian matrix if you want to move on. Okay. Now, so that will be the MLE. And then what do we return? We may return, if you like, just the MLE, or if you just want the parameters, just the parameters. Okay. So let's see whether this will work. It's to remember that the likelihood is just when you have a likelihood function. How do you do it? In practice, you differentiate the likelihood function with respect to the parameter. You set it to 0. And then you solve for the parameter estimates. Okay, so now that optim is taking that function and doing that work you were doing at the undergraduate for you. So that is to solve for the zeros of a function. That's optimization. Because you need the starting point for the parameters. Yeah, so I mean, it's not like the moment you don't need anything. It's just, but for maximum likelihood, remember, that's why at the beginning I said that the way we calculate maximum likelihood when we are doing statistical inference is a bit different from what a computer would do. In the classroom, you set your likelihood function. You differentiate it, set it to 0 so that you find the maximum point. Okay. What the software will do is that give it a function. There are optimization routines. Then you pass that function through the optimization routines. Then it finds what you were doing by setting it to 0 and inverting it like that. So that's how it is done. But it cannot look for. Okay, sometimes it can do it. But if you are writing it from basic principles, you need a starting point. For example, remember when we started, we used fit dist R, right? That you don't need to, because it is inbuilt that if there is no starting point, just use the moment estimator. So it will just use the moment estimators as a starting point. Yeah, but if you are writing it, then you need to provide a starting point. So you need to know the domain of the parameter. Okay, so if you are using exponential, you know that your gamma should be greater than 0. If it is normal distribution, you have mu and sigma. Sigma is greater than 0, okay, or greater than 0, but mu is a real number. Yeah, so that's what I was using to say negative infinity to positive infinity. And in some cases, as I said, you can have a combination of your parameter and the data. A function of it should be maybe greater than another function. Okay, I will show you some soon. Yeah, so when you are doing likelihood, then you need to take into account all those things. So, yes.
Have you seen the optim function? You didn't bring the data to the X.
I haven't finished. Yeah. Just a moment. I want to show you some instance. Why? Okay, what else? Okay, let me move on. It's like it's frozen. Okay, so let's see how this works. Okay. Oh, where did I start all this? Okay, so let's see. The first one, mom gamma. Okay, so we run it. There's no red writings on the console, so it means it worked. Okay. Then the moment I do the likelihood, I do this. But that will not give me anything because I've just run the function. Now I must put it into practice. Okay. So I can sample observations. So we sample some observations. So how can I do that? Well, maybe I say sim data. Sim.data. So I can generate some observations. So maybe this one I start from R gamma, right? So I can go back here. So I'm going to generate observations from the gamma distribution. Then we use the same functions to find the parameters and see what it is. Okay, so I'll show you some. If you are using, so let's say let's do it this way. N is 10, shape equal maybe 2, and then scale is 1, so to speak. Okay, now, so I simulate this observation. Okay, I need to take rate out. So it means here I have to say scale is equal to scale. So that's how you program, so that you don't need to go in to be changing things when you change, especially when you are doing simulation. So I have already indicated what the things should be. So then I simulate observation. So there, these are my data. I can do a histogram of it just to see how they look like. So this is the data, right? Not quite, because it's a small sample. Okay. Then now I need to estimate the parameters generating these data. But of course, we know the parameters is what, 2 and 1, right? Okay, so first of all, we use the moment. The moment estimator. So what do? I put in my data. So 1.41, 0.49. We wanted 2 and what? 1, isn't it? Okay. Then we want to use our likelihood method, likelihood. Pi is missing. Okay. Yeah. Okay. So x is equal to this. So it means pi, I must give it a starting point, right? So maybe I say 1, 1, right? Pi is missing again. Where are we? Let's see. Okay. I didn't finish. Yes. So I did not even put in the data. So x is equal to x. Is that okay? Obtain pi is equal to. What can I do? Let me do this and see. In some cases, it doesn't. Or either you assign it to. Okay, so let me see. If it will work. Now it works. Okay. But it gives us all the. So we go 1.99, 1.0. So you see the same sample size, the same data we put into this. The maximum likelihood is closer to what? The parameter than what the method of movement. And we can do this over and over again by increasing the sample size. So this one, the sample size is 10. I may increase it to 100. We did this. So now this is 100. That's how it looks like. Then we do the method of 2.5, 1.3. So we do the likelihood. If I want, I'll just do the par so that you only see the parameter. So I think they are almost the same. Yeah, a bit, but still the maximum likelihood estimate is better.
So that you know how
Yeah, so this you have to relate to the theory. Of course, if the sample size is small, in some cases the moment estimator is better because the maximum likelihood is an asymptotic. Asymptotically is normal, right? So we don't expect, when we increase the sample size, we will expect the maximum likelihood to do way better than the method of moment. Yeah, so that's what we are experiencing here. If I take, let's say, just 5 observations, that's quite small, right? Okay, so you see the function, the histogram doesn't even look like a gamma. Then we use this. So the method of moments is 1.7. Look at the maximum likelihood. So you see now the method of moment performs better than the maximum likelihood. Yeah, so if I can repeat this, the sample size 5, I can generate several, maybe 1,000 sample sizes of each of them 5, and then that's what we did last week, right? You increase it, let's see. Then we can find what? Bias. Did I see. Okay, I think I haven't, okay, so I think I have not discussed that, so let's move on. So the question is that we've done sample size 5, 10, 100, right? Let's try 1,000. So it looks like this. Now you see that the histogram shows a distribution that is what? Skewed, right? More like what a gamma distribution should be. So that's a moment estimator, maximum likelihood. So still the maximum likelihood is better. Okay, so now I want to see how this looks like. Okay, so I'll do some simulation study to compare these two methods. So how do I do that? Well, I will start first by generating several, like a matrix. This matrix is made up of samples. I can do my samples either column-wise or row-wise, whichever way I want it. Okay, so let's see. So to do that, we can name it maybe n sample, or number of samples. So here I can use S apply. Okay, then maybe, okay, so I want the number of repetitions, so I'll go up there. Let me copy what is there. So now I'll take a sample size, then I repeat. So let me use a small sample size. Let's say we chose 5, right? Then the repetitions are, I'm going to choose, let's say 10. So that's how many times do I want to repeat this experiment? Okay, so S apply, then I generate the sample. So how do I generate the sample? I need to go here and copy all this. Okay, so let's see. So now, of course, it means I have to generate 10 samples, right? Each of them should have a size 5. So let's see. Okay, so when I do this, you see I have a sample 10. Okay, what do I have? A sample. The columns are the samples, And what? The rows are what? The various observations in the sample. Are you okay with that? Please, those online, if you don't understand anything, please draw my attention. Okay. So what we have done, I can show you the dimension. So this should be 5 by 10 matrix. Is that okay? Each column is what? It's a sample. Because the sample has size of 5. So each column is a sample, 10 of them. Good. Now, then I now want to find the moment estimator for each of them. So it means each column, I need to find the moment estimator for each column. How do I do it? So find the estimates of the parameters for each sample. Remember that each sample is in what? Is in the columns, right? So you have a matrix. We are going to act on it for each column. We will find the moment estimator. So how do I do that? I can moment estimate. Moment estimate. I can then use the apply statement. Okay, so I call my sample. Then remember that we said that the columns are what? 2, right? So we put 2 there. Then I just have to call my moment estimator mom gamma. So this, remember that the estimates are 2. So each one I put in will give me what? 2 values, right? So at the end of the day, I'm going to get maybe a 2 by 10 matrix or 10 by 2, depending on how it computes it. Okay, so moment estimate, there it is. Okay. So if you look at row 1, that is I can go back. The row 1 is the shape, and then row 2 will be what? The scale. I can go back here in I think I need to name them. So here, if you name them, then it will be easy, because once you get it, so I can name these values. So if you are naming it, you need to put it into that. Okay, then I rerun it. So when I come back here and I run it, you see that the rows will be named as well, because every one it computes, it names it. So let's see. Remember that I can put all this in parentheses, then it will calculate it, assign, and display it at the same time. There it is. Still, I couldn't get it. It's okay. But we can name it ourselves. But we know that how come? Because it's supposed to name it. Let me do just one and see. How come? I still don't understand it. This is my mistake. I should be returning tab. Yeah, that was strange. Yeah. So now we will see beta and where is it? Named. Okay, here, right? Okay, so alpha and what? Beta. Good. Okay, so now if I apply it to the same matrix, I should have it named. Okay, so you see now we have 10. The first one is giving you alpha, right? What was alpha? Is 2. The first one is 3, then it's 2.5. Then you even get to 100. Yes, because the sample size is just 5. So, from the laws of large numbers, if you increase the sample size, then your estimate will now approach. But if it's something small like that. It can be anything. It can be haphazard. Okay. So that's for the moment. Then we can do the MLE, right? Okay. How are we going to do the MLE? We can do the same thing, but we need to now use a function because the MLE needs some parameters, right? So we need to actually put in a function which will take x. X is the data, but when we call the maximum likelihood function, we need to put in parameter. So MLE, and here I only call for this. So I think it should work. Yes, it should. Let me put this down so that we can see it at a go. Okay, so there it is, like this. Okay, so let me see. Yeah, it worked. So let's see what we have there. Okay, so these apply and these apply, they are very, very, very important, especially when you are doing recursive things. Yeah, so please take your time. I think it was just like 17 minutes in the video. Take your time and watch it so that you see. So I can also name it within the function, right, so that you get it as well. But that means I am only taking out, then I'll leave everything, all the Haitian metrics, and only collect all the parameters, which means I have to come here and modify it in such a way that, let's say, if I want tab, then this will be MLE par. So this will select only the parameters. Then I can name it again just like what? This one. So if you want to get but remember that the maximum likelihood gives us more other estimates apart from just the parameters, Haitian matrix and so forth. But you lose all if you just pick out just the parameter values, okay, or estimates. So if I do this again, oh, I named all of them. Now I can't do this, so I need to take out, because I've already done it in the function, so it can't be true. I need to, this is MLE, right? I made a mistake. Okay, so now I get this, right? And then I can compare it with the moment. Okay, so when I take the first one, this is 3.2, this is 2.1. So the 2.01 is better, right? The next one is 2.01, 2.03. Look at this one, 100. So clearly you can see that the moment is not doing too well, right? Okay. Now what do? We now want to find a bias and MSE. Okay. So in the statistical inference, you can actually compute bias, which is just the expectation of the estimator minus the parameter. The MSE is what? The variance square is variance plus or the bias square. Alternatively, you can find it as or the expected value of what? Theta cap minus theta all square, right? Okay. Then, of course, we can input in the mean of the estimator and then split it into what the bias and the variance. Okay. So how do we do it in practice, in programming? Well, it means I need to now write my own function to compute, let's say, bias. So my bias will be a function. Such a function will need what and what? If I want to compute bias, it needs the estimate from the estimator, okay? So I can say par.est, which is the parameter estimate. Then it needs the parameter itself, so par, okay. Now how do I now compute the bias? How do I compute the
So
expectation?
the predicted minus the actual.
How do I compute the expectation in that?
So they find the mean of the.
Good. Yeah. So you find the mean of the power estimates, and then you subtract what? The parameter from it. Is that okay? It's as simple as that. But this will give you either minus or positive, right? If it is minus, then it means underestimation. If it is positive, then it means what? Overestimation. If it is 0, then it is unbiased. Okay, so in this case, we want it to be close to 0 as much as possible. In some cases, you can find the absolute value of it so that you are only looking at when it is close to 0. Is that okay? Yeah, so bias function. Bias estimator function. Okay, then we need to do that of MSE, mean square error. Now, if the bias is it, then the mean square error will be what? It will be what? So we can take this and square and add the variance, right? That's one way. But we can just find the mean of this all squared. Is that okay? We can find the mean of this. That's also the mean square error. Is that okay? So we could have also put them together if we want. So that is just one function. It computes the bias, it computes the mean. It computes the MSE. Okay. So if you like, you can put this together and call it bias and MSE. So here, I'll just call a function maybe bias MSE. Bias MSE. Then it means I need to open up this function. Okay. All right. Now, this will be MSE. Okay. Then I need to bring the bias. I can go up here and copy. So this will be bias. Like that. And then after that, I can now, let's say, call it tab, and then I have C. If you like, you can even round it off, right? So that maybe they are up to 3 decimal places. So you have it, bias, then you name it MSE, and then round it to maybe 3 decimal places. Otherwise, it will be maybe 6 or whatever. Okay. Then, as we do, what do we do now? We name it, right? Name. Tab. And then this will be your C. The first one is our bias, and then the other one is what? MSE. Is everybody okay with it? Please, are you okay? So this function will take the parameter estimated, or the estimates of the parameter, pass it through the function, but you know the parameter. So for example, what we did, the parameter will go 2, 1. Is that okay? Then it will take each of them and find the means and so forth. Okay. But here, we need to do it one at a time. Okay. I mean, when you are writing, I can do it like 2.
I just did the normal, I just picked the assignment.
Yes.
I just picked the normal, so I just picked all office.
Yeah.
And then name it all office.
Yeah, you can do it that way. Yeah.
And I just place 1, 1. So
Yeah.
I'm not confused because
Yeah. So it's up to you to. Anyway, in program, you do what is, but you know, I mean.
It's very fast because it just.
Yeah, it will just do. And when you finish, you can put all of them into a function. Then you do it, you just give value. So do this simulation, n is 100, this. And then it will run everything and get you your bias. So, yeah, so that's how you should get to validate. Yeah. Yeah, one at a time. That's why we are going one at a time. But you build upon it, and that's the beauty of programming. So here we talk about tab, right? Yeah, so that's it. So now this, I can call this bias man. Okay. Now, so let's see. We can talk about, let's say, let's call, we did the moment, right? So the mom, is it the mom est? What was the, yes, it's mom est and then MLE est. Okay. Now, so it means, unfortunately, we need to calculate the bias and MSE for each of them. Okay. So here, if we take, no, it's 2. So the first row is what? Is beta, right? No, is it beta? No, alpha. Good. So the first row is this. So it means that we are going to give this what? Alpha. Or that's not how we named it. You come here. What? Shape, rather. Sorry. Okay. So that is shape. Good. Yeah. Yeah. So shape. Okay. So this will give me the bias, and actually, I am not. We should be doing it in such a way that it will calculate all of them and then give it like a data frame. That's how it should be. But I don't want to complicate things. The most important thing is to know how to do it, and then the rest of the putting them together, you can take your time to do it. Okay, so this one gives us what? The moment estimator shape parameter. So we get the bias of this. So I can then also call for the bias of the, you are comparing bias to bias and what? MSE to MSE. Yeah, I will not be doing this if I'm doing my work. Yeah, but we are now learning. So let's, okay. So you see up to 3 decimal places, the bias for the method of moment is 11. That of MLE is what? 0.01. Okay. The MSE, this is 980. And you know why? Because of that 100. Okay. This is what? Almost 0. Up to 3 decimal. It's not 0. Yeah, but it's almost because of the rounding. Yeah. Okay. And someone will ask, why is it that the bias, MSE is equal to bias plus variance, and now bias is larger than, because the bias can be negative as well. Okay, so and then you square them as well. So, yeah, okay. Yeah, and we can replicate this for the, that is for the shape. So it means we can also do for what? Scale, right? Isn't it? Yeah, okay. So this is shape and then scale. So here, what do we have to do? We have to change this to what? 2. Good. And then this will be what? Scale. And this is also what? Scale. Okay. So we can run this as well. Okay. And you see now the bias for this one is negative, which means it was underestimating it, whereas this one was what? Overestimating it. And the MSE and so. So that's how you evaluate estimators. Okay. Bias, MSE, and so forth. Okay. So this is basic. The way we went around it, we can do everything together, call it, and then it displays all of them in a data frame format. That's how you should program. Okay, but it's also good when yes, yeah. Then you put them into a data frame and put them in. Yeah, okay, that's fine. Please, any question? So that's how we evaluate estimators. Okay. So now, do we have any? Otherwise, we take another example. Okay, so there's also the other part where, yes, but we did one. Haven't we done? We done one, yeah. Yes. How do you? without using. Oh, so then you have to write down the density of the. So if you come here, so this is your. This is it. So let's say in this case they use so alpha and then sigma, right? So this you have to find a log of this. That's your log. Of course, the product of that. Then you find the log. Then it becomes sigma. So sigma log all this. So this will be negative alpha log sigma minus log what? Gamma alpha, okay, plus log alpha minus 1 log x plus, in this case, it will be negative x over what? Sigma. So that's your log likelihood. So that's what you are now going to use in your a negative log likelihood function instead of the d gamma. Yes. Yes, yeah. If the densities are already in R, you can just go ahead. I don't know. Okay. No, but I mean, you should know from basics because in your project you may not be doing a distribution that's already in R. Or it can be even be truncated. So I think there is one of the questions that I truncate. You've not done the basis, you've gone past it. So let's take a look at the papers I sent you. Okay. Now, yeah, so we are going to talk about the Sen et al.'s paper. Let's go and look at the simulation. It was sent to you online in your, so please check it. Those online, please, are you with us? Or I am mute again?
No.
Okay. Are you sure you are there? I'm sure some will be sleeping on their bed. Okay, so they said there was a meeting and then somebody was snoring and it was part of the meeting. Okay, so the S gamma, the S gamma paper. Okay, so let's look at it. We go to the simulation part. So please, if you have it, please take it. So that otherwise I need to share my screen again. But maybe it's good I share. Okay, so let me re-share the screen. Okay. Yes, so the S gamma. So once I get to, okay, so the simulation study, we are going to do this algorithm. Okay, but the first thing is that we should know how to compute the estimators. Okay, so the estimators, we need to reproduce this table. Okay, in your exam, I'll let you do something like this. So let's see. But as I said, I make sure that you can do it at home before I send you to where a place that is not your home. So let's do it. So this is the moment estimator. How do we write a function to do this? Okay, so please note it. I should have. It will be okay. So the first one is on negative. So those online, I need to be alternating between this and R, but I think maybe I can do it concurrently. I don't know whether you will see. So we need to first write a function to compute the moment estimator. So Sen et al's simulation. Okay. So what do we do? The first one has to be the moment estimator. So mom, let's say we call it mom Sen. Okay, so that what? You are not? Okay, then I need to share all of them simultaneously. I'm coming. Just a moment. So please, you should take the paper. That's what we are trying to do. Oh, will it be able? I want to share them simultaneously, but it seems. Pardon me.
So share the whole screen and you alternating.
Okay, just a moment.
So they have the press. So they have the paper. Let's focus on our.
Okay, everybody has a paper. Okay, so let's focus on the R. Okay, so now I'm taking the what is it? But is there a way to share the? If you can come and help me so that I share all of them, please come.
So unless you share the screen,
You
divide your screen into two.
I have divided it, actually. Come and see. So I wanted to keep it like this, but you see it's sharing only this side. So I should go back and say share.
Share.
This one, screen. Okay, please, can you see all of them? Do you see R and? Okay, good. Okay, so.
Yes, Doc.
Okay, good. So now we are doing the method of movement. So it needs, if you look at it, it needs what? Just the data, X. Is everybody okay? Okay, so we can say X is the data. So the function X. And this is just one function. So I can write all of them at a go. If you like, you can write the numerator, denominator, and then you divide. Whichever one is okay for you. Okay, maybe we should go by that, which will make it easier. So numerator. So the numerator is what? First of all, I have negative times what? Then S bar is what? Mean of X. Is that okay? Yes. Then I subtract 1 from it. Then I go outside the bracket, I have plus. Then square root. So square root is what? SQRT. Right. Then I put into bracket again. Then I have the same thing I did over here, so I can go and call it mean X. I copy and paste. I square it like that, and then I go outside. Then it is what? Plus what? 12 times what? The mean of X. Please, are you okay?
Yes, sir.
And that completes the numerator. Okay. Then I go down, I now get what? The denominator. Let me put it this way so that it makes. So denominator, denom. So that is just what? 2x. So do we need to? We should just divide everything.
By you popularity purpose.
It's okay. All right. Okay. So 2 times what? Mean of X. So you see, it's not anything difficult, right? Okay. Then we can say that the mom is what? Numerator divided by what? Denom. That's all. Okay. And then what do? We return mom.
So you give us the function, right? You write it.
Yeah, definitely. I'll give you a function.
This same function.
This same function.
Okay.
Maybe it's similar.
Let's say you're replicating this.
They say similar and same. Are they the same or similar? So we give you. Okay, so is everybody okay with this? Those online. So that will give you the moment estimator. Remember, we discussed this, and I said you should read about it and then be able. I haven't seen anybody discussing it at the paper review. The question they will ask you, but you read the paper, you answer. Okay.
I think she's yet to do this, so she can.
It is an interesting paper. I don't know why some of you are not there.
Okay, Doc, next week.
Next week you will do it.
Terry is planning to present it, Doc.
Pardon me.
Sheriff is planning to present it next week. Sheriff.
Okay, so let's look at the likelihood function. This is the likelihood function. Is that okay? So this, you can't get it in now to do what? To do your likelihood D so and so. So you need to write it as a whole. Okay. So good. So neg like. So we look at it. They've even given you the log likelihood. The log likelihood function is down there. Yes. But if I'm giving you this, I only give you the density because it's the same. The density is theta squared over. So that's what you have up there. Okay. So neg log like. So let's start. This is a function. And if you look at it, what are the parameters or the things you need in there?
So you need theta, you need x.
You need theta. And you need what? X. Okay. So actually what you need is x and what? Theta. So this one, theta. We can say theta, just theta. Okay. So then we open this. So, so L like is then what? 2. So I need N is what? Length. Length of X. Okay. So then the likelihood I need 2 times what? N times log of what? Theta. Okay. Then minus. We have N times what? Log of what? 1 plus theta. Plus this one will be your sum, right? Log. Then into bracket we have 1 plus, then we have what? Theta s squared, so theta times s squared. Then we divide the whole thing by what? 2. Is everybody okay with it?
Yes, sir.
Okay, then we go outside the summation. Then we have what? Theta times what? Sum of what? X. We are done with this. Please, are you okay? So that's our log likelihood. Remember, we want negative log likelihood because we want to find what? The minimum in the optimum. So we'll return what? Negative L like. Okay. And that's it. That's our neg log likelihood. Okay. Now to finish this off, we need optim, right?
Yes,
Okay. So we're going to find optim, and then pi is equal to theta. Maybe this one, theta is positive, I think. Yeah, theta is positive. We need to go out, but I think it's positive. Yeah, so theta, so maybe we can just give 1, right, for a start. Then Fn, the function is what? This. Like it. And then we pass in x is equal to x, right?
And then the method, sum.
The method, okay. You want sun?
Yes.
Okay.
That one, not specified.
Yeah, sun is quite a good, okay. So that's it. We can get our maximum likelihood. So let's see. This, that, and that one. Okay, this will give us an error because we don't know any x. Okay. So x will be our data. So let's see. But this is not quite good. What do we do? I don't really like when you have to do things like this when you are programming. I want everything to be in a function so that you call a function rather than just this. So we can say MLE dot MLE send is this. So it means we need a function. Then the function must have s and what? Par, right? Then that par we can give it to this one. That's what we did the last time. Is that okay? And then it will give us all the things. If we want the theta, we only select what? Par. We put a par there. Then that will only be, it will ignore all the other things. Okay. So let me do it like this so that we can see everything. So that's our MLE. Okay. So now I'm going to just remember that we have the gamma. You remember the gamma data, sim.data or something. So we can check. But this is it was sim.data. So this is a data set that is not in the same, so the theta for it is this. But we don't know what the theta is because we did not generate it from that distribution. You know, this is a gamma distribution. You are using a completely different distribution to fit it. So the only way, the parameters, you won't know what parameter it will be in this one. The only thing you can check is that you can now get a histogram and fit this density on it. So that's why we did those things. So the density on it will now tell you whether this distribution is actually fitting it well. Is that okay? Yeah. And how well it captures either the tail or not. Okay. So we can also use the MLE to find this. Right? So that we need to say maybe par is equal to 1. So if we do this and it works, error could not find function. I think we had not, then this one we have not done it. Good. Okay. So now each of them we can call this. Good. Okay. So you see we got some. We got it, but it is giving us warning because some of them produce none. Okay. So, but look at it. This one, the method of moment was what? 1.04. They were basically almost the same, right? Let me do it again. Okay. And then this one. So, yeah, you have to take note and see that it is really not an error. Because sometimes it may affect your, but this one is telling you that even though nouns were produced, it was still able to run. Yeah, but it is all, because you are finding 1 plus log theta. Remember that theta will be iterating. And because it is 1, it may go to negative. Because this one, you see, we use sun. So that is simulation. It will be using simulation to estimate it. So if the theta is negative, you will get, and you have s squared. So maybe you get a negative number, and you are finding the log. So that will be a none. But at the end of the day, it will be omitted from what? From the computation. So we can go here and choose the Nelda. Is it Nelda made, right? And see what happens. Maybe that we will not. You see that one, there's no, yeah. So it depends on the method. Because this is simulation, some of the values for theta may be negative, and it renders that part as well and not that. Yeah, you can. Oh, there are clocks over there. It's not working.
The way this one is on this.
Okay. You can take my, I think I have enough. Do it at the time. Okay. Okay. Please, those are the online. Are you okay? So now we have gotten what? The moment estimator, the maximum likelihood estimator. So it means you need to set it.
Yes, sir. We are showing the laptops. Let's come forward a bit.
Okay. Please, are you okay? Those online. Please, are you okay?
Yes, Doc.
Good. All right. Okay, so that is
Yes,
just
Doc.
one part. So now we have estimator for moment, then the MLE estimator. We are now going back to the paper to check what they did with the simulation. So now remember that this was what? A mixture distribution. So it's like two distributions put together. Right. Now, so in that case, you will not find any. And the other reason is that you cannot also invert the x. If you remember when we were in class, I said the x, f of x is equal to p. Then we solve for it, then we get a quantile function. In this case, you can't get a quantile function. So we must find a composite way or another way of what? Generating the observations without necessarily, inverting the function. Is that okay? One way around is to solve it numerically. So what you do is that you bring the p to the other side, then it becomes a numerical problem. So you generate x, and then you get the x that will render that function almost equal to 0 is a member of the distribution. Okay, so that's one way. But another way is to also use mixture distribution generation, which is that we know that this distribution is a mixture of what? A gamma and exponential. So we will take samples from exponential, we take samples from gamma, then we use a criteria to either select from the gamma or the exponential. Then we put them together. They become this mixture distribution. So that's what has been done over here. So first of all, remember that you can generate every distribution from the uniform. Okay. So to do this, they generate observation from the uniform random variable 0, 1. So you generate n observation from there. Then you generate v observation from the exponential with parameter theta. Then wi is also generated from a gamma with shape 3. Its scale parameter is the same as the theta in the exponential. Then, if the u from the uniform distribution is less than theta over 1 plus theta, what happens? We say that we will generate the observation is from what? Exponential. Otherwise, it is from what? A gamma. So that's what you use in what? In selecting. So at the end of the day, you get what? A mixture distribution. So how do we do this? Please, is everybody okay with the algorithm? So every simulation must have an algorithm that anybody can take. That's why we are able to reproduce what they have done, because they have given us the algorithm. Is that okay? So if you are doing your paper review and somebody said they have done simulation, but there's nothing to show you how everything you do in science should be reproductive, right? We should be able to reproduce it. Okay, so if you have not given enough pointers for people to reproduce, that's also a criticism. Okay, so one of my PhD students, you see, and those are some of the things you should look out for. So there was a paper, well, it published in a very good journal. Now, so they proposed an estimator for the generalized Pareto distribution, right? The estimator for the calculating the parameters of the generalized Pareto distribution. Now the principle in that is that you need to get a threshold if you have a data. So let's say I have insurance data. Okay. Now let's say what do you call it? Say retention level, right? Okay. So if I draw a line, then everything over that line I send it to the reinsurance. Good. Okay. Now so it means that every claim greater than that retention level will be what? Will be an extreme value. Okay. In their simulation, they put all the sample together. So that defeats the purpose of an extreme value. Because even the lowest claim is also added to your sample for computing it. Okay, so that estimator, that's all when you use all the sample, but that's not what we do in a script, because we are only interested in the tails of the distribution, not the let's say, if I can also be interested in only the lower part of the distribution, but I can't put all of them together and say this is what I'm doing. So when we repeated the simulation and we were increasing the threshold, we realized that the estimator wasn't performing well. And that's one of the, the strong points of the thesis. In other words, then you should find a way such that this estimator, once it is doing well over here, how do you calibrate it inward so that when you have only larger values, it does well? So that's the PAG, one of the the objectives for the PAG study. So that's how you should be looking at papers as you review some of them. Okay, so now let's see. So here we will be generating observations from the S gamma distribution. So we are going to follow this procedure, okay, the simulation algorithm. So the first one, we are going to do it, when we finish, we can put it in a vector, in a function. So we'll start first by generating U. So U is what? R unif, right? N is equal to what? So we will just do N, because this function, when we want to do it, we need N. So maybe N is 10, right? Okay, what else do we, so N is equal to N, then min is equal to what? 0, and then max is what? 1. Is everybody okay? Okay. So now let's see. So we generate U. So definitely it's a number between 0 and 1. Is everybody okay with this? Okay, good. Now the next one is that we need to generate, so we need to take theta. So maybe theta is 2. Is that okay? Our theta, we are saying, is 2. So which means that's the parameter. Good. If that is the case, then the V will be Rs, right? Exponential. N is equal to what? N. What about the rate? The rate is what? Theta. Is that okay? Okay. All right, okay. Then the next one is what? W, right? So what is W? That will be gamma, right? So R gamma. So that one have what? Shape and then scale. So N is equal to N. Shape is equal to what? 3. And then scale is equal to what? 2. Please, is everybody okay? Theta. So we'll not put it with theta so that we can just be changing theta without if you don't do that, if you change theta to be 10, you now have to come and change everything within it. Yeah, so that's how you do theta. Okay. Then, so first 1, 2, 3, we are done, right? The next one, we need an if statement. Is that okay? So this one, we are going to get 2 over 3. Because theta is 2. So if ui is less than 2 over 3, we said this, else it is that. So just an if statement. However, this thing I always, there's a function, I must look for it. P something. I have forgotten, but we'll get through to it, don't worry. What's the easiest way out? Okay, so let's write it first and then we can vectorize it. Okay, so what we are going to do is that if U is less than or equal to, right? If u is less than or equal to theta divided by what? T1 plus theta, what do we do? Yes, so then x, so I need this. X is equal, so this one I can use if else. Okay, let me do this when I finish. We can use if else this, that. That is quite easy to use. Yeah, so if this, then what? X is equal to what? V, right? Good. Else X is equal to what? W. So that's the function. However, I'm going to do it. You see that it will tell us that because we have a vector, it cannot take all the vector and be comparing like that. There's a function that will do it row-wise. I have forgotten, but I will check but if you forget, there are other ways to do it. Okay. So let me go back and do this. Then, okay, so you say error. The condition has what? Length more than 1. You know, it wants to take one at a time. So I must find a way of what? Passing each of them in there. So when I take U1, V1, and W1, then it goes through. Then I take U2, W2, like that. Okay. So how do I do that? Well, I can, okay, so several ways. I can put them together as a matrix, and then I pick row-wise. That's one way. When I pick the row, the first one may be U, the second column will be V, and then W. So I'll be able to do it that way. Alternatively, you can also write the function, then you take I to run from I as the length of the function. So you take 1, 2, 3, and so forth. So whichever way that's okay for you, you can. This one is what? I can call it maybe, what's this? Maybe set fun. Okay, then I let it be a function. So that function, okay, let me leave this or comment it out so that you know what this is about. Okay, so what I'm going to do is that I am going to say it will take x, if it takes x and theta, that's why I always want you to be very good with functions, because then you can have your way through anything you want to do. So it takes x and theta, okay, then remember x will now be u, v, and w. Okay, so what I'm going to say is that if x1, so it's like a vector, if x1 is less than theta over so and so, let me put, this one will be what? X2. The other one is capital X2. Otherwise, it is what? X3. Do you get what is happening? Okay. So I've written a function. The function takes x. The x are the sample that you've generated from uniform, exponential, and gamma. So every one that I take contains 3 values. Then I check if the first one, which is a uniform value, is less than the theta over so and so. Then I assign it as what? As exponential. Otherwise, it is what? The gamma. So it's the same function we have up there. The only thing I have done is that u is x1, V is x2 and W is what? S3.
So are you supposed to create?
That XX is just the sample. So, okay, I think sum is equal to. Would that be okay? Do you get it now? Sum, okay. Then, after all this, I need to return sample. After all this, I have to return the sample. Let me, okay. Because now I have a function which is doing this. So when I finish, what do I want? Is a sample. And that sample will be from where? For observations generated from that distribution. Please, are you okay? Another way around is just this. So, what I have written there, we could also do if else, this one. So, test. What? I wanted to show you. Or maybe I should use this, the question mark. So, this one is just two alternatives. So, if it is just two alternatives, if the test is true, the next thing is done. Otherwise, the other thing is done. So, what we can do here is that if else, what is it? This is the condition, right? If this condition is satisfied, sum is equal to this. Otherwise, it is what? This. So that what we have written over here is the same as that one. They are both using different values. Okay. But it means that I must put this in the function as well. Is everybody okay? So that's another alternative that you can put in this function. Okay. So instead of all this, let me just say alternative. So alternative will be this. I'll copy this. When you go, you just look at them and the one that you feel. So this one, I don't even need all these things. Once I have this, I just put it here like that. So that's okay. Set alternative. Okay. So let me try this and see. Okay. So this set.fun, I need the first one. Okay, so what I can do is to, so it means I need to put all those things together. So my sample matrix will then be equal to C bind. Do you remember this? So U, V, W. Are you okay? So if I do this, I'm going to get a sample matrix of what? Of size 10. Remember we generated. So I take this. This is my U. I check whether it is less than or equal to 2 over 3. If that's the case, we take this sample. We go to the next one. If this one is greater than that one, we will skip this and do what? And take this. That's how this thing works. Yes. So what we are doing is that what will happen is that it will check whether 0.003401 is less or equal to 2 divided by 3. So this will give us either this is true. So it means it is going to take sample from what? The exponential. Okay. If I take the second one, which is this, I think that will be false. Okay, so I can put that one here. This is also true. So it will only be false if That one is greater than it. Okay. It will take the W. Yeah, that's it. Okay. So once I have this, I can now use set.fan in the same apply statement. I mean, but in this case, I'm going to do 1, right? I think I will need a function because of the 2 values. So function, then here, x, remember x is function, no, just x, but the set.fan, I need 2, and I know theta already. So what do? I'll put them here. X is equal to what? X, right? Which is what we are reading from it. Then the theta, I can just say it is theta. Of course, we know theta already. So let me see if this will work. It did work. Yes. So we have a sample now. Okay, please okay, so here, combine the U, V, and what? W as a matrix. Is everybody okay? Then after that, what do? We apply the set.fan on each row. Remember, each row is the UVW. Yeah. So that's it. It means that my set.fan should be up there, right? And the set.fan, it can be this or that one. If I can, let me say it is 1, right? This one. And then let me put 1 there. You realize that one too will work? Okay. Oh, what happened? Let me see. Oh, no, I need to still, yeah. I need to object X, not function is. Something is not, yeah, it should be like this. Okay, good. So now I can do set.fan 1. There. So they are all the same. Just check which one is easier for you. Yes. Yes.
The if else.
Yes.
X, data X.
Yes.
And then we subset 1, like the first column.
Yes.
Right.
Yes.
And then the first column is U.
Yes.
Okay.
So U.
Maybe the X.
Yes.
Is supposed to be the sample matrix that we've created, and then we subset to 1. So, okay, that's the matrix. But
yeah.
I was thinking maybe it's like a data frame, column 1, column 2, column 3.
Yes. Yes.
And then.
No, but that's why I've taken this. The matrix is made up of rows.
Yeah.
So the 1 means take the first row, the second row, the third row. So each time X will be changing. Okay. As for X is the dummy. The X over here is dummy. I could even put Y there and say X is equal to Y. That will also work. So I'm running that for you to see. There. Yeah, so this one is just something to take. When you are selecting a row, the row must be named. So the name we are giving to the row that is selected is Y. But because this will be changing, row 1, row 2, row 3, what is there is just a holder name or a dummy variable. Yeah, so that's it. So what we have now are observations from the S-gamma distribution. So then now we can now go and estimate the theta. Remember, we know theta to be 2. So if we have that sample, if I now generate S-gamma sample, S-gamma sample. So now we know that this one, the theta that generated it was what? 2. Is that okay? So now I can now go and let me organize this well. Let me take the alternative up. So this one I did not even include. I want to make comments so that when you are learning, it becomes easier. So here, this is a function. So a function to what? To generate observations from the S gamma distribution. I must say that there are so many ways you can do this, so don't just stick to this. So many ways. Okay. Please, are you okay? And then now we combine U and V to be what? That, and then we get our S sample like that. Okay. Now I can call, what was the name of our function for the moment and the, is this ones, right?
MLE.
Yes, MLE. So we can now go and estimate it and check which one is close to what. So here, estimate theta, right? Theta. So what do we do now? We will call this. So we do the moment. It gave us 1.32. What was theta? It was 2. Let's look at MLE. We're still having challenges. 1.22. So it means the moment is a bit better. But this is just 1, right? So what if we want to do this? We need to, where was our, this one? So we need to come here and be generating more observations. So we can generate observations again and see what happens. Oh no, after the W gamma, we need to combine. We haven't, is that the case? No, we need to do this. Wait. We have done so we need this sample matrix. Otherwise, it's going to be the same. You see now, it's like I'm doing the simulation. So I generate it. Then here, combine them into a matrix. Okay, so we do that. What is the next step? Then we need to generate the S gamma observations, isn't it?
So use the second alternative for the second example.
The sample 1. That's what I use.
No, we used the.
So I made a set fan 1 and 2. 1 and set fan.
Oh, okay.
So I use the other one. Okay. So now we have that, we have combined it, then we do that. So that's it. So now generate from S gamma. Okay, then we do that. Before we can now call this. So 0.65. Okay. 0.62. So it's like the maximum likelihood is not doing too well. Okay. So what we can do is to now go and increase this to 100. .97. Okay. What? So if you go to the paper, you can now check. You see what they were doing. They took theta to be 0.1, 0.5, 0.1, 1. So we can be doing that. Let me check this. They did not do 2. So 0.1. Let me see what will happen. Okay. We are still having problems with 1.91, 2.1. So it seems a bit close. But the maximum likelihood is closer than, to 2. But you see, we need to repeat this more than 1,000, then we can compute bias to be able to talk about it. So that's what you see in the. So what we have done is just one generation. So I can go back again if you want to generate. Okay, so now Now we all know what we are doing, so we can put all of them into a function. So that I just run it once and then we get the values. So that's how, but when you are developing it, you must do it from the basis. When you are done and everything is working, now you put them together. So that's it. So let me just call them like this, and then I do it again. Sorry. Because every time you run, it is going to give you different values, right? Okay. So 1.93, 2. So the same thing. So I can rerun it again. Okay. 1.2 to 1.4. If I run it again, I have 1.33, what? 1.54. So it's 1.9. So 1.7, 1.58. So that's how, this is what we mean by simulation. Okay. Is that okay? Yeah. Okay. So you can do this and select it, then you get a, okay, so this average bias, that's what they have done, the average mean square error, and so forth. So that's what they have done over here. So they take beta to be 0.1, then the bias is this, MSE is this. Then they increase the sample size to 40, that's it. They increase to this, and so forth. Okay. So yeah, that's what this is about, and that's an important. So once you finish, then you can now be saying that your estimator is better than some other thing. So if you look at the practical application, they look at the exponential distribution against the S gamma for a particular type, and they show that this one has what? They calculate AIC and so forth. Then it has a smaller AIC, and BIC than the exponential. So it turns out to be a better exponential. But when you are assessing it over here, it has to be on what? The bias and what? The MS. And if you look at it, if you are checking for consistency, you should be looking row-wise because they are increasing the sample size row-wise, right? So let's look at the MSE. 0.66, this was 0.40, this is 414. It's actually increasing. And 0.00. Okay. So when n was large, the MSE was small, right? So you have 0.004, then 0.009. So this is smaller. Then so as the sample size increases, what happens? Look at it. When it is 20, is this. When it is 40, you have that. When it is 100, you have that. As the sample size increases, what happens?
Reduce.
The MSE reduces. What are you witnessing here?
Results to the actual.
So, what is it?
The central limit.
No.
Law of large numbers. So as you increase the sample size, the estimates, the prediction closer to the actual.
This one, well, it's MSE, so it's actually consistency. Remember, when the MSE, as n approaches infinity and the MSE approaches 0, that's what we say that the estimator is consistent. Yeah, so that's what is being demonstrated over here. So basically that's it. And if you are able to do this, then it means that the practical applications, you should be able to do it because you just take the data and you fit it with the gamma distribution, right? And when you finish, you can actually get a density because you now know theta. So you go and write a function for the density. You put theta in, and that would with the data, and that would generate the probabilities for it. So if you plot the histogram and you do it relative frequency histogram, you can fit the S gamma density on it, and then the exponential density on it, and see which one actually fits it better. So this is very important, and that's That's something that I want you to get grasp of it.
So,
Yes.
If you fix it,
Yeah.
how does it look like?
If you fit,
The histogram and the
no, you need to plot it. I haven't, because this one,
yes, I want to know when I see it, how would I know?
how would you, well, I mean, we've done some, but there's no map. If you have the one that is closer to the, so this is what you are looking at. So if I have a histogram, so that's one way. So let's say I have this. Okay. Now, if I have the distribution and its density is, and I have one which is like this, which one is better? The top one, because it is actually getting you the frequencies quite well.
yes.
So that's it. Yeah. So when you generate observations like that, or the practicals, they were using AIs, which is values. But another way that you can use to check is this. Because the data is that you plot the relative frequency, which is the empirical, and then you fit your frequency on it. And then you can talk about it. So if you are, let's say if you are critiquing this is one alternative that you can say that, well, they use AIs. It would have been good that they also, the practical application, get the histogram of it and fit their density on it and so forth. Whatever you get here will also reflect in the AIs anyway. Yeah.
And this is something with the assignment. The histogram showed that the MND was better. But
Okay.
then for the bias, it seems like it was the
Yeah,
instrument.
but that's yeah, it can be contradictory. Yeah.
But I said the graph, the assignment, when you look at it,
Yeah.
look at the method of methods trying to show it's better. But when you look at from different aspects to the ML, it was very confusing. So you can show it to say
Okay.
you
So,
technical.
yeah, so in your case, because you are doing actuarial science, you will be more particular about the tails. Yeah, so that's where your interest should be. Which one actually gets to the tail?
So
In
was
that
the
case,
argument
when there's a large, maybe claim or whatever, this distribution will fit it better. Because here, these are smaller claims, right? Yeah, so, but if something is somewhere here and it happens, it's quite light. So you want the distribution. This one will not give you anything because it actually maybe it will even end over here. So that's the right end point. What this distribution tells you is that you cannot have anything greater than this. So you will be there, this one will come and Bank of Ghana will come after. Or
so if you are using the extreme, then MLE.
so they are almost the same. This is the laws in care. Let's see.
Mine is great. Now, mine is great. This is correct.
So this data is highly skewed.
Yes.
Yeah,
So if you're
it's
trying
like
to look
all of them are, in one box, with the exception of some few. So it's difficult to see which one,
at performance better.
performs better.
So if you're using two criteria first, you're looking at the extremes, you will say that's the MLE. But if you're looking at the one that is on top of the bars, you see that it's the method of movement.
Okay.
Because that one, it's on top of, there's a small bar here. And that one is on top of it.
Yeah,
Yes.
this one is different. So this one, the red one actually goes up.
Yeah, that's how
Yeah.
I asked.
But remember that the MLE2, the method you use also has an influence. If somebody uses the simulation approach and you use the values will be a bit different.
But still, MND does
Yes, my MLE is blue and then you want just red.
yes, it's
You want the key?
Yeah.
Okay. So I think that is a good time, yes.
That's something for me. Oh, sir. So have you seen the work that we did there?
Yes.
When I did when I found the Alpha
So
Investment-
those online, I think we are, if you have a question other than that, we are